Got it. Oh, I don't control that.
Oh, yeah.
So, okay. Oh, yeah, it's on that screen.
All right. Thank you, everyone, for coming today. So, week after Thanksgiving, so it's a bit slow. But we are joined today by Xiaowei, who is a finishing PhD student at MIT working with Rina Nassif, and also Anna Fribo. He has done a lot of work related to Milky Way stuff, including dark matter, also mock observations, as well as a lot of chemical evolution models for dwarf galaxies. And today, I think he'll be telling us about the Milky Way and its dark matter content. So please take it away.
Hey, thank you, Nan, for the introduction. Yes, so as you said, I'm a finishing grad student, and today I'll be telling you about using stars, so the visible things, as tracers for the Milky Way formation. So it's the invisible. I should bring this so that I don't have to go back and forth. Okay. So before we jump into the Milky Way, I want to first take a step back and then just think about galaxy formation in general. From lambda CDM cosmological models, we know that galaxies form through a hierarchical assembly. So starting from smaller galaxies, small structures form first, then they merge together and form larger galaxy that we see today, for example, the Milky Way. Now, understanding this process of hierarchical assembly is really important. In particular, for example, on the galaxy mass function that we usually have, if we look at particularly the low mass end, where there are quite significant uncertainties on exactly what the parallel index should be. There is a lot of things that can affect things there, such as like baryonic feedback, alternative dark matter models, as well as in the context of like a satellite population and tidal effects, that's basically giving us a lot of complication in identifying or constraining this low mass end of the galaxy mass function. Yet it's so important that because it's so sensitive to baryon as well as dark matter physics. So to help constrain that low mass end of the galaxy mass function, we're going to look at things through the lens of galaxy formation, particularly now focusing on the Milky Way. So we want to ask the question, first, in the past, what galaxies have merged into the Milky Way? So if we look at the debris of those merged galaxy population, can we infer any properties of what they were like in the past before they fell into the galaxy? And also we want to look at all the ongoing merger events, so the ongoing assembly process with galaxies falling into the Milky Way. How has that affected the galaxy that's currently merging? So the satellites, also the Milky Way itself, if it has experienced any distortion in its matter distribution. So for understanding that, I'm going to be using stars, as suggested by the title, as tracers to do this study. Namely, why we want to do that is that recent advancement in ground as well as space surveys have given us a lot of data, like that's order of magnitude increase from what we used to have in a lot of different dimensions. For example, astrometry telling us how things are moving, as well as like photometry, just how bright stars are, where they're distributed. And lastly, spectroscopy giving us information about the composition of the stars. That's on the observational side. On the theory side, we now have these amazing cosmological hydrodynamic zoom-in simulations of galactic scale that shows us how galaxies like our Milky Way form and how does that formation process, how is it affected by, for example, different underlying dark matter models or different baryonic feedback physics. Combining those together, this ready to answer some of the questions I listed earlier. Particularly, I'm kind of expanding them here a little bit, and this will be serving as like an outline for the talk today. The first part about the past, what had merged into the Milky Way, will be first looking for these merger debris in the local stellar halo. And once we have identified these merger debris, we'll then connect them to the original progenitor. In this case, we'll be particularly interested in knowing the stellar mass of these past merged galaxies. And for the second part about how things has been affected currently by ongoing merger processes, we'll be looking at two extremes of the mass range. So Milky Way itself, and also the ultra-faint dwarf galaxy that are currently still intact but falling into Milky Way potential, how have their mass distributions been affected by the infall, like the merger process. And lastly, sort of as an outlook, I will talk about a brief kind of future plans on how we can best connect simulations with observations to provide better as well as more robust constraints on Milky Way formation. So moving into the first part here, just again emphasizing that for this part, we'll be mostly focusing on the low mass systems that are currently found in a local stellar halo. Now you may ask, well, if they've already merged now, they're all fixed mix, there's no coherent structure for us to go after, how do we identify them in the first place? So thanks to a lot of the information that we now have with stellar kinematics from Gaia in particular, we now can do this by looking at the dynamical spaces. In particular, if you look on the right here, stars as they fell in with their progenitor galaxy are expected to have invariant dynamic quantities such as total energy or angular momenta or action angle, depending on which dynamic space that you like. But despite having been completely phase mixed, they're expected to still stay clustered as like overdensities in these dynamical spaces. So then we can easily identify them as these little clusters above the Milky Way stellar halo background, and then picking them out and associating them with a particular merger event. And based on those orbital dynamics, so how deep they are in the energy, total energy in the Milky Way potential well, we can even go back and then constrain when did they fall into the Milky Way in the first place. So this is just a summary of some of the more massive mergers that we know today and where did they come from and what their relative infall redshift is. So having identified these mergers, debris, now how do we connect that to the original stellar mass of the galaxy? Now, one classical way of doing this is just look at the average metallicity. So stars kind of act as time capsules that records the chemical enrichment history of their host galaxy. And for more massive galaxies, they will have experienced more chemical enrichment, thus be more metal rich. So if we just look at the mean metallicity of a given population, we can utilize empirical relationships such as the mean metallicity versus stellar mass. That's pretty tightly constrained, and we have it working really well from stellar mass all the way from like thousands to 10 to the 12. That just tells us like where the average metallicity should be given some known stellar mass. And with that, we can then go back now, start putting some data points on the galaxy mass function. So everything seems pretty straightforward and simple. Here's a flow chart of what I just described. But unfortunately, in astronomy, things are never easy and simple, as you probably know from your own daily research. But one thing that we could first put a question mark on is how confident are we with the kinematic substructure identification? Now, if we go back to this slide and then zoom in into this dynamical phase space here, you may wonder, okay, why are you so sure that this is the only way that we can dissect these overdensities, right? This is like just circles drawn on the dynamical space, and you're right to question that. Identifying these substructures in like some kind of in this like overdensity maps is actually a very tricky business. There are two main ways of identifying these substructures, one being like manual selection, and the other one being some kind of machine learning clustering algorithm. Now, doing a manual selection, similar to what I just shown, is obviously not the most optimal way of doing this because different people can do things differently. They can decide to draw a different circle. On the other hand, machine learning algorithm is a little bit more reproducible. You get the same results usually if you apply the same algorithm to the same data. But they oftentimes has a hard time incorporating measurement uncertainties. So a lot of these algorithms, when they were developed in the context of computer science, there's not a notion of measurement uncertainty in those cases. So that's what I did for my first project during PhD, is to look at some of the more popular clustering algorithms and think about how robust they are if we now include measurement uncertainty. So here I incorporated measurement uncertainties into one of the most popular density-based clustering algorithm called HDB scan. And what we found is that while the algorithms are pretty reliable in identifying the existence of these overdensities, when it comes to assigning members to these overdensities, so like if a star it's associated with one overdensity or a different overdensity, or just like should be considered as like a noise in the background, that part becomes really unstable when we start resampling data based on their uncertainties. So here, this is the same dimension of energy versus angular momentum, but only showing the stars that are always consistently linked to an overdensity. And you can see there are a lot fewer of those. Now, coming back to this flowchart, we know that this steps here could be potentially unreliable, but maybe that is not a big issue if we're only after the average metallicity. So having some loss of member stars or a few interloper foreground stellar halo may not be that problematic. Or is it? Again, I'll come back to the metallicity measurement that we have for these systems. If we zoom into the actual metallicity distribution function for every individual one of them, so picking some of the more massive ones here, Sagittarius, the Gaia sausage Enceladus, Helmi stream, Thamnos, what you see is that all of them have this extremely metal core tail down to metallicity of -3. The question here is now, because we're focusing on the low mass systems, how far down can we push this whole like mean metallicity scheme, right? Especially if we consider stars that have maybe say Sagittarius like kinematics, but have metallicity down to -3. How do we distinguish from these two scenarios? Namely that if the star formed in Sagittarius like very early on, and it just fell into the Milky Way with Sagittarius, or if it formed in an even lower mass system, like a UFD, that first merged with Sagittarius and then merged together with the Milky Way. These two scenarios have like completely different, implication on what the stellar or the galaxy mass function would be like. But for metallicity alone, it's really hard to distinguish them. Because after all, like a single supernova can enrich the gas to about -3. So here we have a degeneracy problem that with metallicity alone, there's really no way of telling these two different scenarios apart. To address these two, first we need more robust methodology for identifying substructures, but then also we need to look for better observables than just metallicity or iron over H. I'm gonna address this part first. Here I'm gonna come back to the periodic table, the chemist's periodic table, not the astronomer's H, hydrogen, helium, and just metals. And then think about, okay, now iron is not working, so is most other light elements because they are also abundantly produced in core collapse supernova. That pushes us to now consider heavier elements. And in particular, today I'll be focusing on europium, atomic number 63, which is a known R process neutron capture elements. So these elements can only be formed because of how heavy they are in environment with so strong of a neutron flux that it has been long theorized it's only possible in the scenario of like neutron star mergers. That's no longer just theory. Now we have the observation of GDO 170817 as a neutron star merger, and with all the multi-wavelength EM follow-ups, we now know that these events are indeed capable of producing copious amount of europium elements. And what's more important is that given their rate, how we can constrain them with like GRB events, we know that they're extremely rare. Now, in the context of galactic enrichment, that means for galaxies with stellar mass below 10 to the 5 or 10 to the 6 solar masses, they're expected to have fewer than 1 on average neutron star merger throughout its entire star formation history. That has some really interesting implication on how these europium evolution will manifest in a lot of these systems. So to kind of illustrate that, I'm gonna use this panel quite a bit in the following like 5-10 minutes. I'm gonna take some time to make sure that everybody understands it. So on the x-axis, we just have magnesium or iron over H. So this kind of is serving as a time axis because they're all produced in core collapse supernovae, and because these things happen kind of instantaneously after star formation, so we can use this as a proxy for time. On the y-axis, we have europium over magnesium, so just the number density of the two, but here we can treat it as the time averaged rate of neutron star merger versus the rate of supernova. Because these two are separately predominantly produced by either neutron star merger or supernova. Then we can start considering these two scenarios where in the first scenario, we have one massive galaxy, well, not massive in the sense that compared to a dwarf, so like a classical bright dwarf of like 10 to the 7, 10 to the 6, 10 to the 7 solar masses, and then also a group of UFDs that have stellar mass, maybe like 10 to the 4, 10 to the 5. And very early on, before neutron star merger can happen, you have a lot of core collapse supernova indicated by a yellow explosion or stars here that populated, gave a baseline of magnesium enrichment in the environment. And as time moves on, you started getting your first neutron star merger. Now, for the massive one, it's always going to get neutron star merger at some point in its lifetime. So it's going to happen, and nothing special about it. But for the lower mass groups of galaxy, only a few of them, so here I'm showing one of them, there are a lot of other ones, but only a few of them will get a neutron star merger. Right? So then on average, for every neutron star merger, there will be fewer corresponding core collapse supernova to dilute the gas and then kind of mix everything together. So as a result, you get a much higher European over magnesium in the case 2 relative to case 1. Okay, this is
what happened if you come from a collapse star, this rather than from
yes. I will go into that relatively soon, but in short, is that it will shift everything up.
Okay.
Okay. The fundamental assumption here is that even if collapsar produce europium, they produce on average less europium. Like the yield will be lower from collapsar compared to neutron star merger. As long as that is the case, the net result is that it will just shift everything, the normalization. Okay. Then time moves on. Now you get more core collapse supernova happening in all these galaxies, assuming they haven't been quenched completely. For the more massive galaxy, you still get more neutron star merger and more core collapse supernova. Now, the exact evolution for more massive galaxy depends on what you assume for the star formation history, as well as like the time delay distribution of neutron star merger. But overall, we expect this to result in a net increase in the European abundances for the more massive case. While as for the lower mass system, it's had its own only neutron star merger for its entire lifetime. So now it's only going to get more core collapse supernova, and then hence, instead of it growing, the trend is going down. So here we start to see some interesting and distinctive behavior with the European evolution in these two cases. Now this is the same kind of study done by more carefully with a hydrodynamic simulation, where you see, again, overall an increasing trend for massive dwarfs, whereas like a decreasing trend for less massive dwarfs. The pink points here are measurements from previous studies on one of the merger debris called Ukon in the local stellar halo. And it's known to have a stellar mass before merger of about like 10 to the 8 or 10 to the, about 10 to the 8 solar masses. And here the measurement is showing a very tentative, if you only consider these data points with these data points, very tentative evidence of some kind of increasing trend with magnesium. I know it's very, you're successful, I can see that. And there's reason to do that. Okay, right? If you just like cover this too, yeah, this is just a scan. Right. So overall, the obvious question to ask is that, okay, if we push the measurements down to even lower levels, do we see even clearer trend?
Are you assuming here that you have one neutron star merger early?
Yeah, early in the sense that, yeah, at about,
Well, I would have thought in a 10 to the 5 solar mass galaxy, you might have no neutron star merger at all. And it would just be at 0.
yeah, so, okay, I am not showing what would happen for basically these galaxies, right? Assuming there is collapsar, so there will be some europium in the system, then you get basically some baseline like European abundances and low metallicity, but the general consensus is, at least from my understanding, is that they will be too low in europium, that will be like non-detectable. Again, if they do produce like some amount of process, enough that we will see them in this like even lower mass system, then overall you may get some stars like just lying around here, like just stay here and then yeah, and then however long that they can go, it might just stay flat here down here.
Okay, and it could also take a while for your neutron star merger to happen, like.
Yes.
Over time, so,
Mhm.
later on.
Yeah, so that could also happen. So if you have some time delay combined with an early some collapsar, then you have everything shifted to the right, and then maybe some flat pre-neutron star merger enrichment at very early
You
time.
would see a jump.
Yeah, then you see a jump. You see, oh, yeah. Why did that make that sound? Anyway. Okay, so one more data to verify if this is the case. So we went out and then collected data for a different merger debris called the Gaia sausage, GSE that I mentioned earlier. This is a very massive system that we know today from just its metallicity distribution that is estimated to be about 10 to the 9. So it definitely had neutron star merger. And now it's a little bit clearer that if we consider only this power versus this power, there is definitely an increase from low metallicity to high metallicity. But more interesting is that there is much larger scatter at this lower metallicity range.
The data you have in this other case with silver. Okay, well,
Mhm.
I was just thinking like, how does the data you have there?
How does what?
If I were to overplot the pink points in this diagram.
Ah, yes. So the pink point would be -2, it would be like somewhere here. There seems to be a nice continuation of this thing towards lower metallicity.
Yeah, the scatter isn't so bad.
Yeah, I mean, there is some scatter. Now, we could interpret this as just some intrinsic scattering in the yield of neutron star merger. But there's also a possibility that maybe if we keep pushing down towards lower metallicity, that we will see a bifurcation of the distribution, that we see most of star going even lower in European magnesium. Namely, these are all the stars that form in situ in GSE. And then there are maybe a few stars that will form in some UFD that all the way up there that merge into GSE in early time, and then everything fell into the Milky Way together. Now, why haven't we done that? Well, one, we need to wait for telescope time, but also that there's a problem with the whole selection function. So remember that we have to do this kinematic selection to get GSE star in the first place. And because the metallicity distribution function drops off so rapidly towards metal poor, and the effectiveness of the selection on getting out actual GSE members becomes less and less. So we now start to need to start worry about Milky Way foreground contamination in a sample if we're going to keep going down to the metal poor end. So exactly what does the Milky Way halo looks like at that extremely metal poor metallicity? So here we're changing this to iron, but at really low metallicity, this is more or less similar to magnesium. We just assume type 1A hasn't started significantly contributing yet. But here you see just a mix of everything.
So
Now
we plotted the report.
Mhm.
Are you plotting all the measurements, or are there some that there's just no European detection that aren't showing?
There are definitely some, oh, you mean the previous one?
Yeah.
Like if they have, so for this sample, we have measurements for everything. I think there might be, wait, do I have? No, I think I have measurements for all of these stars. Maybe a few upper limits, but definitely some nothing like crazy low that will tell us that it comes from like a not our processing reached UFDs.
Okay.
So coming back to this, now it's a question how we can connect this mix with this, right? Now we know that it's possible that these trends together contributed to this spread here, because it's kind of nicely lining up with the spread. But there are a lot of complications, right? There's the part where we can't really do a very confident in situ versus accreted separation. The sample selection may be problematic, and we'll also have to consider the fact that we have really large uncertainties on the yield model for neutron star merger in the first place. So while it is promising that our process may be a good element to use to trace for these UFD or merged UFDs. There's still a question mark left on like how can we actually apply it to extremely metal poor star populations. So I'm going to leave that for now. I'm going to come back to it later once we get to the third part of the talk. For now, I'm going to move on to the second question. Before that, if there are any questions about the previous part, besides that question of the intention left. Okay, cool. Move on to the second part. So now we are gonna move on from the disrupted things and now look at more intact things. Specifically now looking at how the current still intact, but ongoing, intact system as they're going through this merger process, how does their matter distribution changes as a result of the tidal interaction between the Milky Way host as well as their own potential. Since we're talking about UFDs earlier, I'm going to start with intact UFDs here. These are, again, smallest building blocks in the assembly process, and we're going to be looking for the ongoing tidal disruption happening in these systems. While these things are extremely faint, you're showing a perhaps not very, now I look at it, it's a little bit hard to read on axis, but this is just showing how many UFDs we've discovered so far, ranging all the way to 200 kiloparsec from the galactic center. Of all these UFDs, we've picked one for a case study, namely the Hercules UFD. I have some of its basic information listed here, but this system is of particular interest to us because of its like elongated shape in the sky. So instead of being roundish, this system has like a roughly 3-to-1 axis ratio, indicating it may have been undergoing tidal disruption, but all the previous studies have failed to find any conclusive evidence of tidal disruption. And what's more intriguing is that they found like the orbital direction of this system is at an angle, so misaligned with the elongation, which is also not typically what people expect for tidal disruption. So altogether, that makes this system really interesting and motivated us to go after it and take another closer look. And again, we're using stars in this case as tracers to understand this potential tidal disruption process. Now, getting stars for UFDs, for intact UFDs, is challenging for two reasons. One, kind of mentioned this earlier, is that the foreground from the Milky Way halo is very tricky in the sense that if we look at any single dimension, so in this case, radial velocity, the member stars of a UFD sometimes are not well separated from the foreground, and that is the case for Hercules. So you have to really incorporate multi-dimensions when you're conducting sample selection. And then also unknown binary system in these kind of UFD system can introduce a factor of a few kilometers per second to extra velocity dispersion. That is not usually a problem with like more massive satellites, if they're like 20 or 30 kilometers per second. But for a low mass system that originally started with like 2 or 3 kilometers per second velocity dispersion, this can introduce a factor of a few biased measurement in velocity dispersion. Again, this is just to address the first problem with foreground contamination. We have selection cut applied on astrometry, so proper motions and distances, photometry and metallicity selection all included, and it gave us about 33 stars in total from over 400 candidates. And for binaries, we have to do multi-epoch observation just to see if there are any significant variation in the radial velocities. And of the 22 stars that we have multi-epoch observations, identified 5 stars that might potentially be in binary systems and remove those from the sample. So here is showing the blue big dots showing the final sample that we have. I want to highlight these 2 stars that were identified in the extended stellar halo of Hercules. They will come in very important in the following analysis. Okay, so what people typically do when trying to classify if a system is undergoing tidal disruption is first to look at the line of sight velocity, so search for any non-zero gradient along the elongation. And second is to look at the velocity dispersion, get an estimate on the dynamical mass, and then use that to then estimate tidal radius. Compare that with the member star distribution. For the first test, we did the fit. Here is the velocity as a function of distances, projected distances along the major as well as the minor axis, just to show that even though these stars at the extended stellar halo helped us get a really long baseline to conduct the fit, the overall result is still inconclusive. If you look at the 2 sigma range of this fit, everything is consistent with 0. That doesn't exclude any tidal disruption, but it doesn't also provide any evidence for tidal disruption. For the velocity dispersion, our new sample gave a much lower velocity dispersion, so only 1.9 kilometers per second compared to previous values that are all around 4 to 5 kilometers per second. We attributed that decrease to the fact that we did this foreground contaminants removal and then also eliminated potential binaries. But the final result is that the dynamical mass estimated for this system within the half-life radius is about 10 to the 6 solar mass. Now that has some interesting implication when we combine that with the fact that we identified 2 stars in the extended stellar halo. If we now take that dynamical mass, assume some underlying dark matter profile, we can estimate the tidal radius, and also not just that, but at its current location, but also like estimate it as a function of its orbital phases. So looking at where it was closest to the galactic center, and thus deepest in the potential well with like smallest tidal radius given the same dynamical mass. What we found is that the tidal radius is only about 0.85 kiloparsec at the pericenter. Now, that alone tells us that these 2 stars in the extended stellar halo may be tidally stripped to their current locations. But it's worth noting that in calculating the tidal radius, we do have to assume some underlying dark matter profile. And that is not necessarily valid if we consider the fact that if this thing is indeed undergoing tidal disruption, then there's no reason to trust, like say it has like an NFW profile. So putting those together, we still haven't gotten any conclusive results in terms of the tidal disruption for the Hercules system. So where should we go next? So now looking back at the question that we had, how has the matter distribution been affected by mergers? We decided to go the other way around and ask the question, well, how should the matter distribution be affected by tidal disruption? So now instead of going from the observed stellar kinematics to the underlying disruption scenario, we now ask the question that if we take Hercules, or a system that's moving like Hercules, and just assume that it is indeed undergoing tidal disruption, how should the stellar track distribute in the sky? Like, if the stream is indeed forming, where should the stream lie? So here we did a forward modeling of stream formation. So all these blue tracks are predicted streams that one would get if the system is like moving in orbit like the Hercules. To our surprise is that these stream actually lines up with the observed star distribution really well. So that misalignment between the elongation and the orbital directions perfectly reproduced. And if we further go back and look at the line of sight velocity gradient that we had earlier, just to see, okay, if the system is undergoing disruption, do we actually expect there to be a 0 or like close to 0 line of sight velocity gradient? Again, here the blue is the model prediction, and the red was our fit, which had like this consistent with 0, 2 sigma range. Again, these two within the range where we have data overlaps. So that's telling us if we now flip the arrow, everything that we observed with the UFD with its star is consistent with the system currently experiencing tidal disruption. So kind of doing this forward modeling, we are now more confident in saying that it is very likely the Hercules is undergoing tidal disruption. Now, this is not the only study where people have implemented such methodology. So Nora Sheep together also with Nan here have done this searches with like simulation data where they look at if we have observations of similar depth as, for example, I think this was like BES. Then when we look at some of these streams in the simulation, which one of them can we actually detect the stream, and which one we will only be able to say that we can see the progenitor and not the stream. And the key takeaway here is that for the Milky Way count, which is the number of streams that we see for dwarf galaxy, everything is consistent once we apply that observability correction. So this is telling us for even more UFDs in the Milky Way, as we keep pushing with the depth of our next generation, for example, LSST survey, we should be starting to see more and more these previously unknown tidal disruption. Okay, so that was the UFD. Now I'm going to move on. Oh, sorry. Oh, okay, never mind. Now, yeah.
So you talked about you have to get rid of the binaries, you got a dynamical map.
Mm.
So are you just taking out things that have velocity variation, or how are you following that?
Yeah, so short answer is yes. So just taking out things with significant velocity variation. So we factor in the statistical uncertainty with like doing the cross correlation on the spectrum, and also systematics from different telescopes.
There should be some with periods of hundreds of years where you still have a 1 or 2 km/s orbital velocity.
Yeah, so those should not introduce a lot of extra velocity dispersion. Here we're mostly looking at the tight binaries that has like this large velocity variation over time. So if those shows up on like so I think the earliest I remember like 2007 or something, if they show a variation on this time scale, then that's kind of indicative that velocity dispersion, that variation will introduce enough extra velocity dispersion to bias the mass estimate.
But I don't think the variation matters, because the orbital velocity in a 100-year orbit is like 3 km a second. And so even if it's not varying during observation, it's still pointing toward you or away from you. And it's more than your velocity dispersion of the galaxy.
Oh, I see. Yeah, I guess for those stars, yeah, we currently don't have any way of telling that that's the case. The hope is that, yeah, if everything, let me think. Yeah, I agree that is a problem. So that even like the 1.9 will be like kind of treated as like upper limit.
Okay.
Yeah. That's like kind of the sad part about UFD dynamic analysis. We start to go down towards, like for example, those wide binaries, and also the systematics on the telescope is kind of usually on the order of 0.5 to 1 km/s.
Right.
Yeah.
Your estimate is already the lowest estimation.
Yeah, it's already a
studies
lowest
as well. So
studies. Yeah.
if you don't remove any of these,
So if we don't remove any of those, then we recover the same kind of 4 to 5 km/s. Yeah. So it's, at least from our analysis, that's mostly driven by these few stars that we see the velocity variation. Okay, so now looking at the Milky Way, here's where I'm going to start move away from lower mass UFDs, just because if we want to have any significant impact on the Milky Way mass distribution, we need something way more massive than the UFD. So here we're looking at LMC. It's like one of the most massive intact dwarf that's currently falling into the Milky Way. And here is a study down recently to see what the infall of LMC, what effect it has on the overall mass distribution of the Milky Way. So here we're looking at something mostly large scale. The R here represent the galactic disk, and most of the distortion we see to the Milky Way mass distribution is on the large scale, so like hundreds of kiloparsecs away from the center. So it seems to suggest there should be a negligible effect, at least from LMC, on the galactic disk scale for the matter distribution. So to test that, we decided to measure the rotation curve or circular velocity curve for the Milky Way and use that to constrain the matter distribution, or in this case, which is mostly focused on dark matter. If we assume that we know the baryonic matter distribution, we constrain that within the galactic disk scale, so within 30 kiloparsec. Now to do that, again, because we're using stars as tracers for rotational velocities, one thing is that we need to know all 60 kinematics. And of those 60 kinematics, distances is always the hardest thing to constrain. Right, so despite Gaia providing us this large amount of astrometric parallaxes data, the precision of those distances start to drop off as we go out beyond 10 kiloparsec. So that's where it run into basically how precise Gaia can measure the position of a star. So to improve upon that precision, we incorporated a precise photometry and spectroscopy measurement, feeding those into a machine learning or data-driven model that learn the relationships between photometry and spectroscopy, which physically should intrinsically incorporate information about the luminosity of a star, as well as like extinction along a particular line of sight, linking those to the underlying true distances to a star, and use that to improve the relative uncertainties on the distance measurements. There are a lot of technical details into like exactly how this is built. I'm going to skip that. I'm happy to discuss that later if you're interested in that. But here's the final curve that we got. Again, it's a velocity curve as a function of distances. The red dots are showing the data points, with the black little arrow bars showing just the statistical uncertainties. So very nice, flat, but after about 15 kiloparsec, we start to see this decline in the curve. This is not something we've been expecting, because if we try to model this curve with a generalized NFW profile, so for dark matter, we find that this profile is having a really hard time modeling that decline. So there is always like a gap between the measurements and the model, telling us that if we assume some NFW profile, even with like a varying inner power law index, it's really hard to reproduce or explain that decline. On the other hand, if we allow things to be changing a little bit more rapidly, so now adopting a Nasto profile with an exponential form, that decline can be reproduced with model. And examining the fit further, we see that essentially what's happening with this decline is that to have this decline shows up at this radius where we see it, we need to have an exponential drop off in the dark matter density outside about 10 kiloparsec. Now, this drop off has some really interesting / concerning implication on the mass distribution for Milky Way. Here is a compilation of the enclosed mass as a function of distances on log scale from different previous studies. If we now overplot our best fit model on the same space, we see that there is a big discrepancy of the outer halo, where at about, like, say, 100 kiloparsec, the constraints from like globular clusters or dwarf satellites, and as well as like stellar stream, is telling us a Milky Way mass that should keep increasing and going up to like 10 to the 11, 10 to the 12 total solar masses, whereas the best fit here is giving something that's completely flat. So the exponential drop off is essentially telling us, okay, there's no more dark matter outside of 10 or like 15 kiloparsec. So the mass becomes a constant as you keep going out. Now it's worth pointing out, now we're starting to get to caveats or like explaining why this is the case, is that first of all, where we have data, so this is the range here in red, where we actually have measurements of like the rotation curve. The discrepancy only starts showing up after we got out of that range. So when we start doing this extrapolation with the best fit model. So obviously there is some question about, okay, is this the best approach? If we just take a parametric model and then blindly extrapolate it and say that this is just telling us, oh, the Milky Way is not, 10 to 12, but instead like 10 to the 11 or 10 to the 10 in total masses. A much better way of doing this would be to employ some non-parametric model that's more flexible. So instead of like going just exponentially kick down, drop off, maybe there's some more complex behavior that's not captured by the model here. But model aside, You may also ask the question, well, why was there a decline in the first place? Could there have been something wrong with the measurement itself? And indeed, there is a potential of a systematics in the measurement, namely that to calculate rotation curve, we started off with the assumption that everything must be axis symmetric, and then there is dynamical equilibrium with the whole system. If there is indeed a merger, like LMC is indeed actually impacting the inner galaxy, these two assumptions will fail. So that's one problem. And also towards the outer disk where the decline is most significant, we have to consider the fact that first, we're only observing the brightest stars at this regime. So these are typically the oldest red giant branch stars. So may have experienced more dynamical interaction with the inner disk. So maybe that could create biases in the measurement. And also, the disk is known to start flaring up at the outer, towards outer disk at about like 20-25 kiloparsec. And that is not really modeled with the current calculation of rotation curve using Jean's equation.
Just more about the sample, where exactly is that located in like this?
Oh, yes.
Is there like a bias? What's where you're observing?
Let me see if I have a plot. I think I might have taken it out in my backup slide, but there was like a one figure that I could show to just show like where the sample is. So we selected just like disk stars that's within 60-degree, I guess, from the solar position, plus minus 30-degree from us. So it's a kind of pizza slice. Yeah.
So I might have misunderstood the measurement, but is this a measurement of the azimuthal velocity? Or is it correcting somehow for the fact that as you go out, eventually things aren't actually moving in a circle?
Yeah, so it is factoring in the azimuthal velocity plus any radial movement. So for things that are moving on eccentric orbits, that's factored in there. Basically, that's what we call like asymmetric drift correction with stellar disk.
So you assume like an anisotropy profile, or are we kind of?
We're assuming a axis symmetric profile. So yeah. What was the question again? Sorry.
Like the radial or tangential anisotropy of the orbits?
No, so there is no let's say like azimuthal variances in the profile. That's kind of the nature of rotation curves, that when we do this like one velocity as a function of radius, we kind of killed off all the potential angular variances.
So I would assume that the Milky Way rotation curve has been well studied.
Yes,
And
past,
why
I
haven't
think
we
mostly
seen
in here, mostly in this room. This is only very recently now with like Gaia that we could go out here. The problem with like doing rotation curve velocity inside of a galaxy is that we don't have the convenient geometry of just looking at the distance from the center and doing only the line of sight measurement, just take whatever is the largest velocity along the line of sight, as we usually do for like extragalactic system. And even for Milky Way, actually, if we just look at the portion like within the solar circle, we can use the geometry to basically only search for things that are moving the fastest away or towards us or away from us in the tangential direction to get the direct measurements on rotation curve. But if we're going to move outside of the solar circle, there you need to have like actual full 60 information. And in the past, people have relied on like standard candles like RLI arrays to do that kind of measurements, or like MESARs, where you have really precise proper motion measurements from radio telescopes. But it's only since like 2018 or so when we have Gaia that we can push this measurement outwards.
But there are measurements at larger distances from dwarf galaxies.
Yeah, those are from dwarf galaxies. Yes, those are separate, and they're like the assumption usually a little bit different. It's either you assume there are some spherical symmetry because it's far away enough from the disk, so you can start kind of treat everything like enclosed mass as like just a ball. Yeah. I think we're approaching the end of the hour here, but I'm just going to quickly say that given all of these caveats, how do we even interpret the curve that we have at hand? Should we just say, okay, this curve is problematic, like there's nothing we can do with it? End of the story. We'll just wait until we get the next generation of Gaia, where it will maybe give us better statistics on the outer disk, and that to the point that we can actually do something more fancy. Well, not necessarily. So here I'm going to go into the last part of the talk about like connecting simulation with observation. First, like introducing this idea of synthetic surveys. This another work that I did this last 2 years using simulations where we imagine if we place a satellite like Gaia into a simulated galaxy such as Fire and ask, okay, if now we conduct a Gaia survey there, what would that satellite see? And that's the result is a synthetic survey, which captures the selection function of Gaia, as well as like our solar position inside of this galaxy, together with like the measurements uncertainties. Taking this, we can go back to this question that we had earlier and now start actually quantifying the contribution of all these systematics on our measurements of the rotation curve. So instead of going from measurements to the underlying mass profile, now we know in simulation what the mass profile is. We can go backwards and start adding all these caveats, see if how much, like quantify how much of a uncertainty do they introduce. So here's some preliminary results, looking at how these different factors play in our analysis or measurement of the rotation curve. First with the non-axis symmetric potential. Now going back to the question about if there is any like azimuthal variances. You now look at the rotation curve, but varies the solar position in the simulation, see how much does the curve that we get varies. And here is like relative deviation from the true value as a function of distances. You can see how it very kind of on average centers around 5% and then goes up to about 15% for this particular simulated galaxy that we looked at. And we can also look at any effects from recent merger, because this is what we're initially most interested in, seeing if any merger will have impact on the rotation curve. And again, this is picking a specific galaxy at a snapshot that we know that is experiencing major merger to see how over time the curve changes. Similarly, with the Jeans equation itself, like how we're not factoring in disk flaring, incorporating all of those, we can now compare the true rotation curve with the curve that we get from like the naive Jeans equation modeling and see how there is typically sometimes, you know, an underestimation at the outer disk. Lastly, how the observational selection function, if we're only taking the brightest giant stars based on the synthetic survey, how does that changes the measurement itself. So altogether, we get a floor of at least 5% systematic uncertainties from all these different sources, going up to 20–25%. And we can do this for not only one galaxy, we can repeat this for different galaxies. And what we found is that, unfortunately, there is a significant halo-to-halo variation in terms of which source of systematic dominates. So that means there is no simple recipe that we could take and then apply it to the Milky Way to disentangle the fact of, say, like a merger event. I just want to quickly also highlight that the same kind of behavior with is a non-careful analysis of rotation curves that's also shown up in the work done by Isabel Sands here with like lower mass dwarf galaxies where the rotation curve is like traced by gas. So again, here is like the same true curve, but if you start ignoring certain factors such as equilibriums or non-circular recovery, actually not, also like magnetic fields, you can start to see like this artificial diversity problem in rotation curve when there is actually none. So coming back to the Milky Way, taking what we learned with the simulation and synthetic surveys, even though we don't have a recipe to disentangle all the facts, we can just conservatively increase the uncertainties for the fit and then ask, okay, now which fit does better? And unsurprisingly, both fit now seems more or less plausible given the same data. And the problem, and at the same time, we see that one of them, so for inesk profile, it is still preferring a more cored dark matter density, while as now the GNR NFW profile is giving a more cuspy prediction for the center of dark matter.
Ask
Mm.
about this again. I mean, imagine like you do away with all of the physics motivated, but you just look at your wedge where you say you have data. What's the effect of angular resolution? Would there be any way you could, like, in non-parametric way, pick up those deviations?
Yeah, so what we did with the initial calculation was that we tried just slicing our data into like 2 halves and use that as like a estimate of how big of like angular variation could be. So there, well, at least from the Milky Way data, we saw the uncertainty is on the order of like a few %. So it's like actually similar to what we found here in the simulation. So this is kind of like from simulation also kind of verified that was the case, but we didn't know, for example, some of the facts such as like the time dynamic equilibrium factor, those we can't really constrain from data, like the observed data itself. So coming back to this picture, there's still much to learn about the Milky Way density itself with like modeling issues and stuff, and trying to figure out a better way of modeling of like getting the rotation curve. But I want to just quickly, now we are officially running out of time, say that we don't have to stop at rotation curves, right? We can take the same methodology or like logic and go back to say, for example, this case where instead of going this one direction, we flip the arrow and then now use synthetic survey to predict what the R-cross enrichment should look like. Now bypassing the need to like actually dissecting the samples into like in situ versus secreted versus different certain like merger event and just model everything together to compare the distribution, like what things look like. And also for like UFDs, forward modeling, even though we've already have this stream formation track in place, and look at how if we can also combine foreground and binaries together into synthetic survey. And lastly, it's just right now time here, let's just say like maybe we can skip the step of getting a rotation curve once for all, and then just map directly from the dark matter distribution to the observed. So kinematics, leave that as summary slides. Thank you for your attention.
We are actually out of time, so any very quick question, or feel free to catch Xiaowei after the talk as well.
All right, thank you.